really quick. But if you guys got questions or comments, just wave a hand or throw a tomato and I'll stop and we'll take it from there. But wow, I'm thinking back to a time long ago in a land far away. I was at the radio club and my friend Mike had a 2-meter HT made by Standard, and it had a click rotary switch for a channel selector, A, B, C, and it needed a crystal for the transmit frequency, a crystal for the receive frequency. And whoa, we don't really have anything like that today, do we? Because our 2-meter HTs have got phase lock loop synthesizers giving us hundreds of memory channels, priority scan, band scan, all these wonderful things that we just couldn't get with crystals. Phase lock loops I've found are a little difficult to understand, but not impossible. They're made up of blocks, of sections, things that you probably already understand. So here's the plan. Let's take a look at some stuff that you already know, figure out the blocks that we need for a phase lock loop, put one together, see how it works, get it to work at radio frequencies, take a look at some developments in technology, and then when we understand how they work, we can understand how they don't work and what we need to do to fix them. Okay, let's get going. Yeah, we need one crystal oscillator. Yeah, I know we're trying to get rid of this transmit crystal and receive crystal, but we still need one crystal oscillator, one really good one. That's the reference oscillator. We like crystals because they've got wonderful stability, and we can put a trim cap in the circuit and tweak them right on the button. We don't like crystals because they're expensive, they're fragile, they're big, well, some of them are, and yeah, they can get to be kind of a pain. In contrast to that is the VFO, the variable frequency oscillator, with the frequency determined by inductors and capacitors, one of them being variable. We like VFOs because they can be adjusted over a wide frequency range. We don't like VFOs because they've got bad frequency stability. And the higher up in frequency you go, like 2 meters, the more difficult it becomes. And here you can take a look at what Collins Radio Company has done to try to come up with, this is a permeability tuned oscillator. Sealed unit, do not remove. If we can get this off, we can take a look at what Collins has done to try to come up with a good stable VFO. Okay, that's a Hartley oscillator, 2 inductors, 1 capacitor. Yeah, actually it's a tapped inductor, but it's still 2 inductors. In contrast, this is my favorite, the Colpitts oscillator, which has 2 capacitors and 1 inductor. One of them is variable, like, yeah, like this one right here. That's the tuning capacitor. That's the big knob on your transmit VFO. Let's focus in on that, because what I want to do is take that out of there and put something else in its place. I want to put a varicap, a variable capacitance diode, in place of that tuning capacitor. Everyone knows what a varicap is, right? Okay. So you probably know this is how it works. In a diode, when it's reverse biased, when the voltage goes the other way, the charge, the area of charge moves away from the junction. And the greater the reverse voltage is, the farther this area of charge moves away, as I've tried to demonstrate by the increasing number of backwards batteries. As this area of charge moves, well, these areas of charge are like the plates of a capacitor, as I've tried to depict with the green thing above the diagram there. So as the voltage increases, the plates of this capacitor move farther and farther away. So voltage increases, capacitance decreases. Okay, so we're going to take this and we're going to put this right into that Colpitts oscillator like this. Okay, well, we need a way of getting the DC voltage in there, so we've got to run it through an RF choke and put a bypass capacitor on it. A couple other things. Oh, the DC path, the RF choke keeps the RF stuff in the oscillator and allows us to put DC in without messing around with it. There's a block to the DC path on that capacitor above the varicap, and hopefully there's a block of the DC going to the cathode or grid circuit or emitter, going the other way. Okay, so now we've got a VFO, except we don't have a dial. I can take my variable voltage power supply and hook it up to this point right here, the one that says VCV. Oh, you'll see this symbol a lot. Control voltage, VCV. Motorola calls it the steering line. There's a couple of other names for it. But I can take my variable voltage power supply, hook it up to that point, put a frequency counter on the rest of the circuit, not shown, but just pretend it's there and it works. As I increase the voltage, okay, the plates of this capacitor, this varicap, are moving farther away. So as I increase the voltage, I decrease the capacitance. As I decrease the capacitance, I increase the frequency. Okay, pretty much all VCOs are like this. You increase the voltage, the frequency increases. Now, if I was given an infinite number of parts, I could probably come up with a VCO where I put in 1 volt, I get 1 megahertz out. 2 volts, 2 megahertz out. 3 volts, 3 megahertz out. Well, let's say that I have this. This is one of the blocks that we need for the phase lock loop. So here we are. We've got our voltage-controlled oscillator, 1 volt in, 1 megahertz out, 2 volts at 2 megahertz out, like that. Okay, so let's just put that off to the shelf, the side for a second. Another thing I need is a phase detector. Now, there's all kinds of different phase detectors. The one that I want is, I put 2 signals in, and I get a DC voltage out that's proportional to the phase. One real good example of this is, let's say that this blue signal is 10 megahertz WWV as being received by your HF receiver, and this meter is the S meter on your receiver. So here's this signal. Now you come along with your frequency counter with its 10 megahertz time base reference, and you're going to tweak it right on the button. Okay, what will happen is, here's the signal, and you get your frequency counter there, and it starts shaking back and forth, hopefully not too fast. And then you tweak it, and it starts slowing down, and at some point it's going to stop. So then you've got 2 signals that are the same frequency, but maybe a slightly different phase. What I want here is similar to that. Okay, because when the 2 signals are in phase, they're going to add, and you're going to get a high indication on the meter. As they start to cancel and go out of phase, then the signal decreases. What I want is kind of the flip of that. I want a phase detector where the DC output becomes greater as the phase difference becomes greater. So, okay, let's say I got one of those. That's another block that I need for the phase lock loop. Another thing I need is a low-pass filter. An RC filter will work just fine. I want to take the output of this phase detector and, well, amplify it, and then run it through this filter, because I want really, really pure DC. A resistor around a meg, well, let's say 820K, and like a 0.1 microfarad capacitor. Now this capacitor has got to have really good low-loss dielectric, because it's going to have DC on it, and I don't want this DC bleeding off, or anyway, it's got to be real good. The result, I want to have, good clean DC, like your power supply would have. You guys all know about logic circuits and highs and lows and flip-flops. The toggle flip-flop is a fairly common one. Imagine you have a train of pulses, like from a clock generator, and you run that through a toggle flip-flop. It'll pretty much have the effect of cutting the frequency in half. It's like one what's the exact definition now? One change in output for every 2 changes in the input. So you get a high and a low, and then, oh, you guys know how that works, right? Okay, in JK flip-flops, you can chain them together to make a counter. If you have a serial shift register, you can clock in data and then latch it and then run it to the sets or the resets and get a programmable counter. I think most of us know how to do that, understand that. But one thing I'm going to show you here is a scenario where a radio signal, a radio frequency AC, goes into a logic circuit. Okay, well, I can take a diode and slice off the bottom half. I can take a comparator and square that up and get the 0 to 5 volt or whatever I need. So just imagine that. There actually is a circuit where you can throw in a AC radio signal and get highs and lows. I'll show you that later. But I think that's pretty much what we need to get a phase-locked loop together. Here it is. There's the description, but here's the picture. The reference oscillator, that's that 1 megahertz crystal. We can come up with that. 1 megahertz crystal oscillator going into one side of the phase detector. The output of the phase detector is going to go into a DC amplifier because I need to get the voltage up to the point where I can do something with it, like throw it into a low-pass filter. That's the RC filter, the resistor capacitor that we saw. Now, there's a test point there, that funny-looking thing. That's a test point. That's the VCV test point. That DC voltage goes into the VCO, the voltage-controlled oscillator. Remember that? That's the 1 volt in, 1 megahertz out, 2 volts in, 2 megahertz out, that one. And there's a feedback path because the VCO signal not only goes out to what we're going to do next with it, whatever that may be, but it also goes back to one of those inputs of the phase detector. So yeah, that's what we got. A 1 megahertz crystal oscillator, the phase detector, the DC amplifier that kicks the voltage up to the point where we can use it, the RC filter, and then the VCO, yeah, 1 megahertz or 1 volt in, 1 megahertz out, and then the feedback path. Okay, let's turn this on and see what happens. Okay, power on. The reference oscillator is going to be cranking out a 1 megahertz signal. The phase detector is going to be doing all kinds of things, but it's going to be charging up that capacitor in the low-pass filter. At some point, that DC voltage can get up to 1 volt. And at that point, we're going to have a stable operating state, believe it or not. It's like this circuit likes to do this. What we'll have is the VCO generating a 1 megahertz signal. Now that goes back to the phase detector, where the crystal oscillator is also generating a 1 megahertz signal. The only thing is that there's a little bit of a phase difference between the two, enough to create a 1 volt signal from the phase detector. Okay, is that it? Yeah, the reference oscillator is putting out a 1 megahertz signal. The phase detector is flying all over the place, charging up that capacitor. It gets to 1 volt. The VCO puts out a 1 megahertz signal. It goes back to the phase detector. It goes back to the phase detector. Same frequency, slightly different phase. And then the phase difference is just enough for a 1 volt signal. Now, this might not seem all that great, but actually it is kind of significant because now we've got this sloppy inductor capacitor VCO generating a signal that's just as stable almost as the crystal oscillator. So that's actually pretty neat. And here's how it does it. Let's say that the the VCO wants to start drifting, which it will, and it wants to go to a higher signal. Well, as it tries to go to a higher signal, the phase difference is going to become less. The phase detector is going to put out a slightly lower voltage, and that's the same thing similar to cranking down the VFO dial to compensate for the upward drift of the VCO. Going the other way, let's say that the VCO starts drifting and it wants to generate a lower signal. As it tries to do that, the phase difference is going to become greater, and the phase detector is then going to put out a higher voltage, which is the same thing as like cranking your VFO dial up to compensate for the drift going the other way. Okay, let's go through that one more time, because we're going to do something here. Okay, the VCO wants to generate a lower frequency. The phase difference starts becoming greater. The phase detector puts out a higher voltage to compensate for it, which will increase the frequency of the VCO. Okay, what I want to do here now is this purple thing. That'll be the flip-flop. Okay, I'm going to throw that in the feedback loop. What's going to happen is the 1 megahertz signal is now a half megahertz signal. That's like a really, pretty severe drop in frequency. That's similar to what we just saw, except to a much greater extent. Well, the phase detector still wants to see a 1 megahertz signal here and a 1 megahertz signal here. That's actually possible. That's something that could happen. Remember, our VCO, if it's got 2 volts into it, it'll put 2 megahertz out. Well, if it does that, if it puts 2 megahertz out, it'll go through that divider in that feedback path, go back to the phase detector as a 1 megahertz signal. Well, now we've got a VCO putting out a 2 megahertz signal. There's a little bit more phase difference at the phase detector, but that's pretty cool, because now we have this thing with the inductors and capacitors and the varicap. This VCO is now putting out a 2 megahertz signal. Now I can also, let me put a programmable divider in the feedback path. Well, now, just like with that flip-flop, I can do a divide by 3, divide by 4, divide by 5. I can do divide by 3 and get a 3 megahertz signal. Divide by 4, get a 4 megahertz signal. Divide by 5, get a 5 megahertz signal. 6, okay, on up to, 8 or 9 or 10, depending on what the varicap in the VCO can handle. And some other things to consider here at radio frequencies. But now, with this circuit, I now have the same thing as like I don't need a 3 megahertz crystal or a 4 megahertz crystal, 5. With this circuit here, I can get all of those with just this one circuit here. Okay, well, we're still not up to our 144 or 146, but we're getting there. We want to generate signals in actually like 5 kilohertz steps. There, we can generate signals in 1 megahertz step, but I want to be able to program a frequency like 146.415. Well, that 5 is 5 kilohertz. 5,000 cycles per second. Yeah, why did I have this example here? Yeah, if you wanted to generate a 100 megahertz signal and you had a 5 kilohertz reference oscillator, you would need a divide by 20,000 in the divider, which will give you a multiplication of 20,000 times. Well, now, 5,000 cycle per second reference oscillator. Well, that's like an audio frequency. The only thing is that if there's 1 cycle per second of error, we get a 20 kilohertz error at the output, and yeah, we don't want that. So we need something really, really stable. And of course, we get that from the crystal oscillator. one thing that was real common back in the good old days when they had like fixed divide ratios and divide numbers inside the phase lock loop chip was a divide by 2560 with a 12.8 megahertz crystal as the reference oscillator. And come to think of it, that's maybe what this is here. But 12.8 was a real common reference oscillator frequency. If you figure 8 JK flip-flops to divide by 256 and then a symmetrical divide by 10, that'll give you that. So yeah, that was real common. You'll actually see that in some of the older radios. Another one of the problems we had, we're still trying to get up to 2 meters now, is the highest radio frequency that the divider can handle. Back in the good old days, what TTL could handle up to 30 megahertz, low power Schottky could handle like up to 50. That's getting close to 6 meters. CMOS wasn't very good. We had emitter coupled logic, which we'll get to in a second. But another thing that they used to get around this problem of the divider and the highest frequency that the divider can handle, they put a local oscillator and a mixer in the loop. Okay, and everyone knows how super heterodyne receivers work. Here I have the example of your 93.7 FM radio signal that you want to listen to. Your receiver's got a 10.7 megahertz IF. Your local oscillator is 83 megahertz. Okay, well let's throw that in our phase lock loop. Let's say that's local oscillator there is 144 megahertz, and we have a 5 kilohertz reference oscillator. Well, now we've got 144.005, 144.010, 144.015. That'll do it. And this is one of the things that they did back in the good old days when they did not have fast dividers and they didn't want to use ECL. The low-pass filter, I already talked about this. Yeah, the RC filter works pretty well. The resistor is on the order of a megohm. I think 820K was real popular. The capacitor is 0.1 microfarad. It has to have really good dielectric, mylar, polycarbonate, I think polystyrene, a couple others would work real good. There's also other things that you'll see in this low-pass filter, not just a resistor or capacitor. There's sometimes a notch filter tuned to 5 kilohertz to get rid of the remnants of the 5 kilohertz reference or whatever it might happen to be. There's other arrangements of resistors and capacitors that'll give you a second order response rather than first order, things of that sort. So that's one of the things that you'll see in real radio phase lock loop synthesizers. Oh, another thing that can happen with this low pass filter, we're going to want to change frequency from time to time. And when we do that, the low pass filter can be kind of a problem, especially if we want to do it fast, like in band scan or memory scan. We'll want to change that voltage across that capacitor. And since it's a capacitor, it doesn't necessarily like its voltage changed across it, at least not real easily. And especially if you have a high value, 1 meg, 820K resistor. Well, one way we could do this, like if we want to do a frequency change, go to a different memory, is have a push button that would momentarily short out that resistor and give us a real fast voltage change. One of the things that you'll see from time to time is a transmission gate across that resistor, and the microprocessor will temporarily enable that and connect that when there's a new memory channel next in the band scan, things like that. So you'll see that from time to time. Phase lock loop chips also have a lock detector. It's a high, low. It tells you whether or not you've got a lock. If you don't, it's like, you know, you really don't want to transmit, or you're going to be receiving garbage. The microprocessor can use this lock detect for any number of things, like turn on a little red LED when it's out of lock. You open up the radio, you see that red thing there, and you say, oh darn. So that's another thing. One of the things that I didn't show on the block diagrams is the buffer amplifier on the VCO. Just like your VFO, you know, you've got your VFO tube and your cathode follower tube. The VCO needs a buffer. Oftentimes there's two of them, one of them that drives the next stage and the other one that drives the dividers in the loop. So you'll see that from time to time also. Okay, so far we've seen examples of how a phase lock loop generates a sine wave. That's great for a local oscillator in a receiver, but at some point we're going to want to frequency modulate this thing and turn it into a transmitter. Just as DC goes to a varicap, audio can be used to frequency modulate a VCO. Some of the old crystal oscillators, like Mike's standard 2-meter HT, those crystal oscillators use a varicap to get FM. Often this is another varicap placed in parallel with the one in the oscillator. There needs to be a little bit of DC bias to keep it, you know, in the reverse biased state. And hopefully the audio signal is going to be symmetrical because it'll move the carrier frequency up and down by the same amount. That's something that we got to consider now in the phase lock loop, because there's that low pass filter. Hopefully that low pass filter will not react quickly to the change in audio. That's why the values of resistance and capacitance have to be chosen to keep this in mind. Otherwise, a change in audio could be viewed the same as a drift in frequency real fast. Low frequency audios like PL sometimes have a bit of a problem with this because the loop will tend to diminish low frequency audio. One of the ways they get around this is to frequency modulate the reference oscillator, and then hopefully the loop capacitor is able to handle that. But you'll see that from time to time too, where the PL goes to the reference oscillator. Okay, more developments and improvements in technology. Of course, they put all these things onto an integrated circuit, a chip, the dividers and counters, the phase detector. You can even put the VCO on the chip. Some of the Wi-Fi wireless things have all that stuff right on the integrated circuit. Here's one, the reference oscillator. Remember that reference oscillator has got to be real nice and stable. Well, one thing they can do is put that on an aluminum oxide substrate, put it in a can, have a little trimmer capacitor, and you've got a real nice reference oscillator here. Yeah, it's real nice, but it's also real unrepairable. You want to fix this? I don't know what's wrong with it. I also don't know what's wrong with these other ones here that I have, but I have them because they don't work. So, nice idea, but not real repairable. Okay, I mentioned that there's all kinds of phase detectors. This is one of my favorites, the sample and hold phase detector. It's the same idea as the sample and hold that your DMM uses, where your signal can be varying and thing like takes a picture of it so that it has a nice stable solid signal to work on. This is how the sample and hold phase detector works. It's got a current source and a capacitor to generate a ramp, similar to what a oscilloscope has. So there's a current source charging up a capacitor, okay, and then there's another capacitor. It's like having a push button switch. You know, we can like take a picture of it. What we can do is get this capacitor charging up, generating a ramp voltage, and at some point we press that push button. We've got the same voltage on the sample capacitor as we do on the hold capacitor. Or no, the same voltage on the hold capacitor as we do on the ramp capacitor. That's what I wanted to say. So that's how that works. This is the sample and hold phase detector. You'll see this from time to time. It's a Motorola creation. Here's the waveforms. Okay, this is kind of how it works. Let's say that the switch is closed to start out with, so the voltage is 0. Well, the reference signal will come along, a rising edge, let's say, and open up that switch. We start getting this ramp being generated. The VCO signal will come along, generate a sample pulse, same thing as like just pressing that push button, and then we get that voltage at that point on the output. So yeah, that's the sample and hold phase detector, one of my favorites. I'll tell you why later. But another one is the charge pump. This is pretty common. Also, you'll see this from time to time, another Motorola invention. The idea is that to change the voltage on that capacitor really, really fast, we could have something like this where we press this button if we want the voltage to go up, we press that button if we want the voltage to go down. And here's a circuit that'll do it for you, right out of the Motorola data book. The chips have two outputs. They're called, what, phase R and phase V? I don't know why. But most of the time they're at a logic high, and they'll pulse to a logic low. I put this circuit here just for reference. I've never seen one of these go bad, by the way. It's pretty simple. And let's see, yes, of course the VCO is a sensitive circuit. Oftentimes it's shielded like this. Oftentimes it's in a can on an aluminum substrate. Here's an example of one. This block that you see, this big thing, that's the VCO. That's the voltage controlled oscillator. A lot of times the inductor is actually a strip line, laser trimmed to get it right on the nose. Real nice, but of course real unadjustable and real unrepairable. If it goes bad, sorry, you got to replace it. Oh, here's another advancement, the dual modulus prescaler. Ah, what a horrible word. Dual modulus prescaler. Oh, don't let it scare you. It's a two-number divider, okay? Dual modulus prescaler, when you see that, think two-number divider. That's what it is. A real common example is the divide by 15, divide by 16. You see that in a lot of radios. And the input to that actually is a radio signal. And it's got the diode to chop off the bottom, the comparator to square it up. And it's an ECL emitter-coupled logic chip. It's separate from the phase lock loop chip because if you can choose whatever divide ratio you want for whatever application. They give you the freedom to do that. So it gives the designer a lot of flexibility. It's kind of scary. This is how it works. All the stuff in blue is on the phase lock loop chip. The purple one is the dual modulus prescaler. Oh, this is typically like an 8-pin chip, tiny little 8-pin chip. All you need really is, voltage, ground, um, input, modulus control, and output. Okay, that's 5 pins. So yeah, 5 will fit in an 8-pin package. And this is kind of scary to understand, but go to the Motorola data book if you really want this to get a better idea. But this is how it works. First of all, the dual modulus prescaler dividing the signal from the VCO by P plus 1. In this case, it's the 16 rather than the 15. Okay, the N and A counters, they're both counting down from whatever they were programmed in. As soon as the A counter hits 0, okay, that's this bottom one, oops, that's the bottom one here. As soon as that A counter hits 0, the modulus control changes from low to high, and the prescaler 15 instead of dividing by 16. And it's going to keep doing that until the, what is it, the N counter hits 0, and then the whole thing starts over again. The total divide number is actually A plus N times P. Oh, and of course, we've got the divide by R, the reference oscillator divider, that's in there too. That's on the chip. Okay, that's kind of scary. I'll go into that later, but yeah, the dual modulus prescaler, what a wonderful chip. Also on some of the older radios, I mean, now we've got I2C integrated circuit communication. We've got SPI, serial peripheral interface. Back in the good old days, they had, shift registers, so you need to clock your data in, and then the enable is a latch. So you'll see this from time to time also on some of the older circuits. Adjustments. Okay, this is how to keep things going. I showed you an example of the reference oscillator instability causing a instability in the frequency output. And from that you might be able to determine that the reference oscillator controls the frequency of all of your channels. So the owner's manual, the service manual will typically say something like, set the radio to a known channel and tweak that reference oscillator until that channel frequency is correct. It varies from one radio to another, but typically that's how it goes. So if you're off frequency on one channel, you'll be off frequency on all of them. And that's something to keep in mind if you ever run across that problem with your radio, all off frequency one way or the other. It's the reference oscillator. Another adjustment is the VCO range. The example I showed with that little test point sticking up there, that's the VCV test point. That's actually pretty important and especially for troubleshooting. VCOs often have a range adjustment. The inductor or capacitor can be made as a trimmer or a variable, not something like this in the can, but the adjustment for that is pretty typical. Pick a channel in the center of the band and adjust the VCO adjustment for a voltage in the center of its range, whatever that might happen to be. And of course, use a DMM. Don't use an analog volt-ohm milliamp meter, because that's actually a pretty low impedance. That'll pretty much short out the signal, and it won't work, and you won't be able to do the adjustment. Another thing you can do is, let's take the radio to its highest frequency, like 148, and take a look at that control voltage. That'll be 8, 9 volts. I can take that range control and I can crank that up to maybe 10 volts, 11 volts, 12. It'll still be in lock. But then I go to a low frequency You know, I go to 144 and I go back to 148. Well, it won't be in lock. That's because capture, there's two performance characteristics of phase lock loops. One of them is the lock range, the range of voltages where the loop will actually be in lock, but then there's the capture range, which is much less. So that's one of the things that you got to watch out for, is just because you can tweak it and get it up there doesn't mean you're going to be able to get it back next time around. Oh, of course, if you've got a radio that's got a problem, you know, like no transmit, no receive, the troubleshooting procedure can be similar to that of your standard HT with its crystal oscillator. One of my favorite things to do is to get an HT, tune it to the transmit frequency, key up the microphone. If you can hear yourself and if you can receive a signal, then your phase lock loop is okay, and your problem is somewhere else. Some radios are real nice, and they'll have a display, and it'll display out of lock or synthesizer error or something like that right on the front panel, and that's based on the lock detect circuit. As I note here, you can use your HT to see if you can hear the signal. Another real simple thing is, you know, check the programming, and if you can reset the microprocessor, you know, reset the radio, give that a try, because that might actually work. I've run across this a couple times. How about you guys, where the radio doesn't work, something's totally goofy, you reset it and everything's fine. You just lose your memory channels, that's all. Yeah, I've that's happened to me a couple of times. Just reset the microprocessor.
Isn't
Yeah.
that potential? I mean, I know exactly what you're saying about that. I understand the reset process and all that kind of fun stuff, but I guess I'm like insanely afraid of doing that because I have something in my little head that says when they tuned the radio, they went through and there's a little adjustment here, a little adjustment there. So there's something in the radio that says, oh, when he's tuning between these two frequencies, this is your reference number, shall we say, like a 2 in memory, shall we say, that the circuit uses to get the correct frequency. When you crank it up a little bit more, it's not going to be double that, it might be 3. So there's these little tweaks to get it just right where it is because there's some fluctuations are going on, and you're going to lose all that information by doing a reset where you're going to have to go through and do this very complex process to get your radio to tune from one end to the other perfectly or whatever like that. I mean, I don't know for fact that that's what happens, but that's what I'm afraid of. Do you know what I mean?
Well, I'm afraid of that too. I'm afraid of other things. It's like, you know, I really don't want to press that reset button, but I think, well, you know, I've done everything else and I can't figure out what's going on here, and everything else seems to be okay. Give it a try. But I know what you're saying. Some of these operating parameters might be stored in a flash memory somewhere, and yeah, are you going to lose that, and is that going to cause problems?
Most of that's stored in EEPROM, though, isn't it?
Yeah, some of that.
Depends on how
yeah,
good
some
that
of
reset is. I mean, the reset might go through and just, oh, let's wipe all that out too. You know?
I ran into this 48 hours ago where my Motorola DMR radio wouldn't take a program on the active zones anymore. So I had the option of radio recover, and I got a pop this morning that you'll use Moto Tuner as a service monitor to bring the radio back.
Oh,
Okay, I'm not going to do that.
Okay, so it looks like technology has progressed to that point.
Depends on whether we set the calibration rate.
Well, anyway, if you think that it's a phase lock loop problem, one of the first things to do is get your DMM out and check that VCV test point. There's usually like a hole in the can for it. That'll tell you a lot, because that should be a stable DC voltage. If it isn't, and you don't have a lock detect indicator, that's one thing you'll see. If your DMM is doing something funny and you think, oh gosh, you know, I do have a problem, get out your scope and take a look at that VCV test point. If it's flying all over the place, yeah, then you've got out of lock problem. So that's why that VCV test point is there, not just for adjustment, but for you to tell whether or not it's the phase lock loop or something else in the radio that's causing your no transmit or no receive problem. Well, one of the more common failures, as you can obviously tell, is the reference oscillator, by the fact that I've got all these dead reference oscillators here. One of the things you can do to tell if the reference is good or not, like 12.8 megahertz, I can take my HF rig, my general coverage receiver, dial up 12.8 megahertz, take the antenna off, plug in a cable with a little pickup loop at the end of it, get it close to that, and I should be able to receive a 12.8 megahertz signal on my receiver. Otherwise, if you think it's okay, but you can't really tell, an RF probe, a scope, other things like that can give you an idea of whether or not the reference oscillator is working or not. Let's see, I think what did I put this in here for? Yeah, with the digital multimeter, check your VCV test point. You can see what's happening. Yeah, hold on here. Oh, okay, yeah. The VCV test point, that voltage can give you an idea of what's going on. It's entirely possible that your VCO is good, your dividers are good, your low-pass filter is good, all of those things. Yeah, why did I put this in here? Yeah, if you have a spectrum analyzer, you can sometimes see a signal flying all over the place like this. With your receiver, you can sometimes pick up noise. That'll tell you that the VCO is working. It's just not in lock. One of the more common situations that you'll run across is your radio will work on high channels but not low channels, or it'll work on low channels but not high channels. Well, that's because the capacitor or inductor in the VCO has drifted and it's out of range. That's why they give you that adjustment so you can get it back into range. Yes?
So I've been looking at some old Motorola Astro portable radios, and they do the laser engraving on the inductor to tune that radio in there when they're shipped out. You get to feel out the lock on a particular band.
Yes.
I want to reband the radios. You know, they might be at 460 megahertz. I want them to work at 440 megahertz. The guys that work at the Motorola factory in Phoenix are telling me, get your silver solder pen out, and it's quite a process. But I read online, somebody said you can use a pull-up or pull-down resistor on the VCV input. Basically drop an SMD resistor and pull the frequency and move a radio in the band that it operates on. And it's contradictory information, but I'm wondering, do you have any thoughts about?
Yeah, I can see where that's possible because an offset, offsetting the VCO voltage that might work. I'm thinking of some of the E.F. Johnson radios where they actually have the inductor, it's a strip line on a circuit board. They have these little actual like solder jumpers, and if you need more inductance you can solder, make a little solder bridge across this tiny little point. If you need less inductance you can take your cutter out and break them. So there is that also.
Yeah, I don't have access to one of the radio ships, but I understand that there's a window during manufacturing. They shoot a laser through the window to attach the inductor.
Wow. Yeah, I can believe that. Yeah, especially for UHF and higher. Yeah, laser trimmed strip line is not uncommon because coil and core type inductors get really tiny. So I don't have any experience with that, but I wish I did. It sounds interesting.
Yeah, I want to bring a couple of radios here, and you can help me get these peeled out.
Okay, I'll bring my laser.
And I'll bring my ball fumes when you're so frustrated.
Okay, another thing you can do if you think that there's a problem with the VCO, consider that resistor in the RC filter. If you can lift one end of that off the circuit board, you can take your variable voltage power supply, go in right at that point, and play around with it and see. Some radios actually have a troubleshooting procedure that defines how to do that. I remember some of the Motorola service manuals had that. It's like, disconnect this resistor, put this variable supply on the steering line, and then, take it to 1 volt, take it to 9 volts, and get your frequency counter out and check to make sure it's within range. So you'll see that. Oh, and of course, you guys already know this, but if you think that, like, your VCO is out of range, you get, like, doesn't work on high end, doesn't work on the low end, and you're going to go in there and tweak that inductor, you've got a line on your fiddlestick adjustment tool. Remember where that line was, because if you tweak your coil and it doesn't do anything, and then you forget where it was, well, now you've got 2 problems instead of 1. So you just keep that in mind.
Been there, done that, got the ball peen out.
Yeah. Oh, here. Oh, I remember this. I mentioned that this capacitor in the low-pass filter has got to be a really good one with really low-loss dielectric. One thing that can happen is this capacitor can get leaky. Like if there's a crack in the encapsulation, there's, moisture can get in there from humid air. Solder flux from soldering, it'll migrate, and all of a sudden your dielectric is conductive. The typical scenario is that channels on the high end of the frequency range will not work. And then if you think maybe it's a range adjustment, as previously described, you'll get in there with your alignment tool, and the voltage will start going up, and then it'll stop. And you keep on turning that adjustment, and it just doesn't go any higher. So if you run across that, it's entirely possible that you've got a bad capacitor in the low-pass filter. I've seen that happen a lot. Oh yeah, and of course, putting a jumper across that series resistor is another way of getting an idea of whether or not this is the problem or not. Also, if you do a tap dance on the capacitor with your insulated alignment tool, sometimes that will indicate this is it. This is the part. Again, just a little bit of leakiness or failure in that dielectric will cause this problem. You can take that capacitor out of there, put a new one in, it'll work fine. You go back, you check this with your multimeter, and it will indicate just fine. Check it with your component tester. Well, if you've got one that indicates leakage, that might help a little bit. But oftentimes the capacitor will test out just wide open many megohms with your handheld DMM. The same thing for the sample and hold phase detector. Now that going back to the sample and hold phase detector, you guys remember that constant current power source charging up the capacitor. That's like 100 picofarad capacitor. Because remember, this happens 5,000 times every second. If that capacitor has got a bad dielectric, you'll run across the same thing. And it'll drive you nuts because you might think it's this other capacitor when it's really this one. I ran across this the first time. I want to see what's happening on that capacitor. I put my scope probe on there. It's noisy as all heck. The voltage doesn't go up to where it should be going. It's because the capacitor is bad. Put a new one in, works fine. Yeah, what do I say? Yeah, check the voltage at the hold capacitor. Yeah, I guess you can do that too. Okay, for the charge pump, you know, I've never seen a charge pump phase detector go bad. The thing to look for is, you know, a high at those two outputs, either with a DMM or a scope. If you do have a scope, you know, the only time you're going to see them go low is when you do a channel change. Most of the time they'll be high. If they're pulsing like mad, you know, it can do that if the reference oscillator has gone bad, for example. So don't let that fool you. And if you ever do run across one of these that's gone bad, let me know, because I've never seen it happen. The dual modulus prescaler chip, the two-number divider, remember that's an ECL chip, that's emitter-coupled logic. It'll actually feel kind of hot. You put your finger on it, it's actually warm. Even in handheld portables, that's probably the hottest chip there is. Often, as I mentioned before, there's a buffer amplifier that drives that. If you got two of them, make sure that both of them got output. I've seen it before when one of them is bad, and it's like the one that drives the divider. So yeah, make sure that you've got the radio signal at the input of the chip. If it's going bananas, if it's out of lock, you'll still see something coming out of it. You'll still see the square waves. The phase lock loop chip counters, dividers, will still be dividing, so you'll still see that modulus control. It'll just be kind of like an unstable square wave. So, yeah, I've seen these go bad. The dual modulus prescaler, typically there's like no output. The input is there and there's just no output, low all the time. Oh yeah, the microprocessor interface, the good old one from the good old days with the clock and the data. Yeah, you can look at those. And of course that only happens during a channel change. You can see the data, you can see the clock. The clock is actually the easiest to see because there would be a blast of square waves. The enable, you know, it's like a high going low or a low going up. That's really hard to see. But oftentimes that won't go bad. Almost done here. Another problem that you can run across is called VCO microphonics. This is in radios like your HT, where your speaker and all the rest of the radio are all in the same thing, or your mobile rig with the speaker in the cabinet. What will happen is that you get like a howl, a squeal on receive, and people will tell you that you have a rumble when you transmit, especially if it's a mobile rig. What has happened is that the VCO shield is acting like a microphone, and it's picking up sound, it's picking up vibration. The typical cause of that is that the shield is loose or not making good contact. If it's one that's screwed down, make sure that the screws are tight, or else just take the whole thing off, clean it up. Same thing, the circuit board going onto the radio, the landing pads, the grounds. Take the circuit board off, clean them up. I like using Scotch-Brite and alcohol. Otherwise, you're, technician in a can, spray, maybe fine sandpaper if you really want to use that. A wire brush, yeah, maybe. Oftentimes, for something like this, only way to fix it is to get out your soldering iron and reflow all those solder connections. Okay, well, that's just about it. Now, in your radio, whatever you're working on, there's all kinds of different configurations of phase lock loops, and if you have a real old Kenwood radio like mine, the receive phase lock loop is actually in the feedback path of the transmit phase lock loop. There are radios where there's a receive phase lock loop and a transmit phase lock loop, two separate ones. There are HTs where the phase lock loop controls both transmit and receive. Your transmit range is here, your local oscillator receive is down here, and all kinds of different things. So, yeah, what you run across, there's all kinds of different things. The reference oscillator. In some radios, that reference oscillator also feeds the second local oscillator and second mixer of your receiver. And sometimes that goes through a tripler or a multiplier and something like that used as the first local oscillator. There's all kinds of different variations of that. So look at the manual, look at the service instructions. They're all going to be a little different, but those are the common ones, the things that you'll see. For phase lock loops, again, the common problems are reference oscillator is dead, VCO is out of range, and microphonics. Don't let this happen to you. And if it does, hopefully I've given you some help in how to be able to fix them. Okay, that's it. Any other questions? None?
Good job, Jim.
I just have one question. How long did this run? How long did it take? 9?